lecture content, I now assume it's being displayed in at least 1080p, which is a problem because I've like gone back and watched some videos in like 720p and like the text is garbled a little bit and stuff, right? So like all of the stuff I make is useless on a non-HD monitor. But like if I couldn't just assume everyone had an HD monitor, I'd just do things differently probably. And separately, since this is a markdown file, I can just like recompile it if anything ever changes. What are we doing? Oh, so I think at the end of last class you were all accusing me of cybercrime. Wasn't that true?
I think so.
I don't think there were any accusations, just facts.
There's a lot of questions to the effect of like, why are you so good at committing cybercrimes? And which cybercrimes have you committed? When did you stop committing cybercrimes? What is your favorite cybercrime? Okay. And that was basically related to this slide. But I think this is where we ended last time, at ed25519 algorithm. So I'm gonna sketch this intuitively first. Okay, this is an attendance incentive because I don't feel like turning on my webcam. You imagine there's a curve. This curve corresponds to numbers, right? Because we can imagine that it's on the graph, right? So this is 47, which hits the curve right here. It's an elliptic curve, so there's multiple points on it. We often say, hey, it's over some field. What does that mean? Well, you just cut the curve at some point, basically. And this isn't literally what you do. This is a good way to think of it. Sorry, the markers don't work. Well, wait, no, there's another green over here. I'll try it. And you say, okay, well, I'm snipping my curve. And I'm basically doing it with modular arithmetic, so I can actually just displace this portion of the curve back over here. So from here, I go up at like about this angle, and then I'm incident again, then I clip over, and then I'm like at lower angles, right? What's this mean? This means that when I start clipping my curve, there's multiple curve points that correspond to different numbers. That's all. So this is a way to take one number and turn it into another number. So I can say like, hey, I'm at like this position on the curve. I need to encrypt that somehow. No problem. Push it up to here. And then, without knowing the field size, it's very difficult to know what this number corresponds to. So if someone knows where these bars are, it's easier to reverse the curve, and otherwise it's not. That's basically what's going on. Is that a great explanation? No, I mean, I think the elliptical curves are like a lot less intuitive than some of the other ones, because you're going back and forth between having infinite numbers of values and having finite numbers of values a lot, and I find that a little bit confusing, but that's what's going on. We're just trying to find corresponding locations on curves, and they correspond under different ways. So I wanted to make this as easy as possible, so I thought I would just say what we're doing. In public key cryptography, Edwards curve digital signature algorithm is a digital signature scheme using a variant of the Schnorr signature based on twisted Edwards curves. And I think we all understand what that is, so I'm just going to keep going. I liked this formulation, which is that an Edwards curve digital signature algorithm, signature, and they say scheme, so protocol, perhaps, agreement between two parties. It is a choice, and it is a choice of a bunch of numbers, and the numbers impose restrictions on each other. And when you have a satisfying collection of numbers, you're able to sign things in a convincing way. So the first choice is we take a finite field, which we denote as sort of math fancy script F subscript P. In order for it to be a finite field, we need P to be prime. We want P to be prime for other reasons. this distance here is what I think of as p. So I'm going to take a subset of the numbers, of the natural numbers, right? And I'm going to take a subset of prime size. Because it's of prime size, it's not a ring like our earlier things were. So U8, U16, U32, those are rings because 0 is divisible. Because I can take half the size of the ring, multiply it by itself, and get 0 back, right? Is that right? It's something like that. So there's a square root of 0. I can multiply two numbers together and get 0. That's not true with prime fields because there's not any two numbers we can use to hit that 0 that is a prime number away from 0, right? So we're going to pick an odd prime. My understanding of mathematics, I don't know, like the politics of the term prime in mathematics is, in the very early days of mathematics, I thought 1 and 2 were both considered primes. It became really degenerate to consider 1 a prime in a bunch of proofs. Now there's a large number of proofs where you don't really want to think about 2, so everyone just says odd prime all of the time. My vote would have just been to kick 2 out of the primes, because they're a social construct anyways. But anyways, you can't use 2. The problem with this is, like, no one's using a prime of, like, any reasonable size. We're talking about, like, several hundred digit primes, right? So why don't we just say a large prime? And that, like, no matter how large it is, in order to be large, you can't be 2 because that's the smallest prime, right? So anyways, what is a finite field? I'm introducing a person's name and a technical term for a very specific reason here. I'm going to read this slide and then I'm going to tell you the reason. In mathematics, a finite field, or I believe Galois field, so named in honor of Évariste Galois, it is a field. A field is a type of mathematical object. It's like a set. It's a set with operations. It's a field that has a finite number of elements, not infinite, so it is not the reals. As with any field, a finite field is a set on which the operations of multiplication, addition, subtraction, and division are defined and satisfy certain basic rules. Those 4 operations are, of course, the requirements for X. The most common examples of finite fields are the integers mod p, when p is a prime number. I don't know how I got double p's there. I don't know if that's a rendering issue. Okay. Oh, I was going to plug in my computer. I'm going to do that now. Am I going to do that now? Okay. You have an assignment while I plug in my computer. And it is Google Galois Portland. Or DuckDuckGo, for those of you that are thinking you can get away with it. I think there's data structures going on across the hall. I don't want to walk over there. I like data structures.
I like how for some reason the auto page description is an image description.
I don't make the rules. So before class, I came in here, sat down my computer, then went into my office. I was thinking oh, I need to go get my charger because I'm low on energy. And then I went into my office and ate a Cliff Bar because I was thinking I referred to me, the physical human. And so now my energy level is fine, but that did nothing to help my laptop, right? So what I actually need, right, is a hand crank on the side of the laptop. So as long as I have energy, the laptop's okay. This was founded by a Willamette alum. In the early days at Willamette, of Willamette CS, I'll say, many of the computer scientists that work here, and in fact this was a common trend across the United States at the sort of smaller undergraduate institutions were programming languages people. And the programming languages people got made fun of a lot by the software people. And so it tended to be the case that the programming languages people, even if they went into industry, they would form their own companies. Galois is one of these companies. The most wealthy and powerful of these companies is Jane Street Financial, who's been like crushing everyone by doing things that make sense for about 30 years. Now they have an infinite amount of money. Anyways, I was going through undergraduate in like the 2010 era, and like the programming languages people were like a punchline because everyone was using Java, which was the worst language that was ever made, right? And they're like, if everyone's using Java, why does programming language theory matter? It's like we broke all the rules. Anyways, then in 2020, something happened. All of the software people went home, and there wasn't a manager around to make them use Java anymore. And then Java died. It's gone. No one can find it. We don't even know where the body is, right? And so, anyways, after sort of around 2020, when a bunch of programmers actually got to use good languages again, all these companies that were around sort of at the periphery of the field for a while, people noticed that they had been doing things that made sense for a long time and had dramatically higher skill at writing languages that weren't Java. Galois was one of them, and they picked up a ton of contracts in that era. This was pretty good for the local economy because we're not like a super high tech-oriented economy in this area, so Galois is like one of the big ones. Anyways, they have internships basically every year. Now, there's a fundamental problem I have to solve, which is they want to use good programming languages. And by that, I think they mean Haskell. Now, I have shown you Haskell in this class if you were looking up during the lab last week, right? I haven't ever taught you Haskell. I don't think someone else in the department could teach you Haskell, and it doesn't really make sense for me to teach you Haskell. But if you look this place up and you want to work here, probably collect a few more math classes and ask me if I want to do an independent study on Haskell or a functional programming language. I've been skilling up on functional programming languages for some time, and now that Rust is a thing, which is brand new, it is dramatically more useful to learn a functional programming language, such as Haskell, Lisp, Racket, and ML are the big ones. This place also, I think, uses Rust, so we might be okay now. I was in consultation with this company when I decided to teach Rust this year. So this might be a place you can work. Probably do not send out, or you're welcome to send in an application, but if you are interested in working for this place, probably what we want to do is go through career services and see if they can contact any of the lumps there. And so look into that. So take a look at these options and take a look at other ones. So it's not just these people in Portland. RivOS is out there. They're not alumni founded. NetSpy has some alums at it. So there's a variety of companies like this. But one of the reasons to bring up Galois fields is you can be like, oh, Galois, that's named after the field that I learned about in this class. And like that will help you in the job interview. Okay. People say I teach formal mathematics for no reason, but in fact, I just gave the reason. Okay. Oh, one other thing. Please get jobs. Like, probably you want jobs already, but also remember, don't think of yourself so much. It's also good for me, right? The UNs and INs in Rust are rings. I believe there's supposed to be a space there, but like already, by the time you're saying code U, math script N, regular character S, this is already just not grammar, right? No one should be allowed to type things like this. I was shocked when I typed this in and it showed up at all. So UN for all N and IN for all N in Rust are rings. They have addition and multiplication and, I guess, other stuff. They aren't fields because 0 is divisible. And specifically, if you perform the divide operation inside a programming language, it won't work, but the mathematical divide operation is inverse multiplication, and we can find two values that multiply together to get 0. So math doesn't care what your programming language thinks the divide operator is. It thinks it's the inverse of multiplication. So we are still breaking the rules. But the trick I'm using to get a 0 divisor there is not allowed specifically for prime numbers. So I'm introducing this notation, which is a common way I have seen the rings represented, which is you take the integers and you divide them by the number times the integers or something. There's some intuitive sense for how to understand this that I knew for the 10 weeks when I was taking the class when this was taught in undergrad and then forgot forever. I've seen other ways to stylize this, but I believe it's stylized this way at this university. Does anyone know? Has anyone seen this in a math class here? Have you seen it stylized another way? Okay. So I think this is common. I've been trying over the course of the past few years to standardize my slides to how the math department does things, just so we don't have like two competing standards at one university with like 7 faculty at it, right? So anyways, if you ever write this down and someone's like, what are you doing? Complain to me and I will fix it. I have never seen in my life anyone put an expression here instead of a number. I'm willing to take the fall for that one. I do not think this is more clear if I write 256 there. That is very much 2 to the 8th because it is an 8-bit value. And I express this the same way. So I'm pretty sure this is a prime number. This is 257. And it's a special type of prime number. Ah, yes, it's the second largest known Fermat prime. What are Fermat primes? A Fermat prime is a prime of the form, how is this expressed? 2 to some power plus 1. Why is this useful? For a pretty complicated reason. Fermat primes all have the same Hamming weight, which is the Hamming weight of 2, which is the minimum Hamming weight, number of bits set to non-zero, for an odd prime. Fermat primes are very interesting because if you want to implement multiplication times a Fermat prime, you can do it with 2 bit shifts, which means it is as fast as addition. So this is a very special prime field for that reason. That's not on the test. That was on the test last term because that's RSA relevant, but that's just a fun fact. Okay, so let's get back to where we were starting from, which is EDDSA. We take a finite field, and then we're going to take an elliptical curve. Why did I say elliptical? Elliptic curve. We're just going to call that bold, italic, capital E. It's not math script. And we take that curve over the finite field. Specifically, it's a twisted Edwards curve. I spent a few weeks looking at the definition of twisted Edwards curve and have given up. But basically, they are a plane curve. So that is a curve in a planar space, so we can think of any number of dimensions. The planar space is within a finite field, so it is not an infinite plane. For example, if I think of the XY coordinate system that I was graphing things on last class and also like in middle school, that was an infinite one. I'm taking a subset of that. It's a plane, and it can be a hyperplane. There are different forms. This seems to be the most popular form, where we have something times x squared plus y squared equals 1 plus something times x squared y squared. And the most popular EDDSA, ed25519, is exactly of this form. Okay, what is a plane curve? Planes are things that are flat. That's all, right? Y equals x is a plane of 1 dimension in the 2-dimension coordinate plane, or a plane of 2 dimensions in a 3-dimensional coordinate plane, or something like that. I want to show that you can think of this as a graph of a continuous function. So I just went and I threw an elliptic curve inside symbolic Python. I converted it back to literals, and then I graphed it in NumPy. This is an example of what an elliptic curve could look like. This is an ellipse, so not a particularly exciting elliptic curve. And I don't think this is necessarily a classically defined elliptic curve either, right? This is not of the same form that we were using earlier, but we'll visualize some of these later. This code should run on your computer. So if you want to investigate these, you can go ahead and plot all of these functions. I wanted to provide you a plotting library. Why is that? Well, in the olden days, when I was trying to understand mathematics, I would go to Wolfram Alpha and try and plot things. There were a few things I tried to plot while making this slides that I couldn't get Wolfram Alpha to do, and this seemed to work pretty well for me. You can try Wolfram Alpha if you want. I haven't used it for a few years, so I might not be good at using it. But this is literal code. This should run directly on your computer. You may not have these libraries, 3 and 4. You almost certainly have 1 and 2. And it's not too hard to get SymPy. You should be using SymPy all the time, is my impression. Okay, so an elliptic curve E over the finite field, whose group E of FP, what is a group? A group is a set with multiplication, I believe, of F sub P rational points. This is where I gave up. I don't know what rational points are. I can't figure them out. Has order. So there are how many points? There are a certain number of points on this curve that can be expressed with rational numbers. We take the number of those points, and it is 2 to the power C times L. So it's a power of 2 times something. What is that something? It is a large prime. I don't know how the C got in there. It's a large prime. And 2 to the C is, we just call that the cofactor. But what we need is we need a power of 2 multiplied by a prime, and we need to have that many fractions in our number system. My recommendation, if you don't understand this, is to take a 400 level math class. I don't even know if that will help. I think that will help. But basically, this is a measure of how much ellipse you have. I say area within the ellipse here. It's the surface area. So it's like how many points are on the curve that can be described by fractions, which is not all of them, right? So at some point on this curve, something is pi away from the origin. I can't define that with a fraction. But at some point on this curve, something is 1 away from the origin, and I can't define that, right? So there are points on this curve that can be defined sort of using finite numbers, and there are points that cannot. And so I need the ones that can be defined rationally. There is also a base point. Base points are unique to someone generating the signature. So when we are using the digital signature algorithm, by default, your expectation is someone gives you an elliptic curve, they give you a prime field, they have already calculated this somewhere else, they have already proved properties about it. In the case of the most popular one, they demonstrated that it runs faster than any other known curve on Intel CPUs, which is a pretty useful thing because it can do 64 calculations at a time using Intel vector ops, right? So someone went out and they picked out the very fastest, the very safest elliptic curve, and they give it to you. And then what are you going to do? You're going to pick any point you want within reason on the curve, and that is going to be your base point. Now, there are a lot of points on the curve, right? There are, in fact, 2 to the power C, which is going to be some large power, times a large prime, which is also a large number. So there's going to be a lot of points on the curve. That's basically your level of security. Someone has to guess which one of these base points you have in order to figure out how you are generating numbers. You also need a hash function. This hash function has to have 2 times b bit inputs. And what does b have to be? B has to be large enough to store the prime value. That q is supposed to be p. Dang it, I thought I got all of them. For some reason, the reference text I was going off of here was using q for primes instead of p, which I found recklessly confusing. So I tried to change all of them, and I missed that one. So you have a number of bits you need to express your prime value. You must have a hash function that can generate hashes of up to that size bits. That hash function is SHA-512, which is going to produce hashes of size 256, or 512. Okay, so someone gives you the curve. They give you what numbers you're working with. You pick a point on the curve, and you already have SHA implemented on your computer. This is actually pretty close to what you have. You have the big integers, and you have SHA already. So, what are we going to do? I'm going to introduce a series of terms, and these series of terms are going to enable us to describe portions of EDDSA. There's the public key. Who remembers what the public key is? The public key is the number that Glenn Greenwald put in his Twitter bio so that Snowden could send him illicit information, right? So the public key is something you can share publicly. People can use it to encrypt information, and only someone that knows your base point can turn it back into the original information. So the public key is a curve point. What does that mean? Just means somewhere on the curve. Some place on the curve. You express mathematically that location on the curve, and you put it in your Twitter handle. It is encoded in B bits. Then we can perform signature verification. So, signatures, and I described these earlier in the context of Bitcoin, where the message is, I pay someone X amount of money. So, I'm going to take a message, and I'm going to use the public key as well. So, in order to express both of that, I need two things. I need R and S. Why are they called that? I'm guessing these are the letters after something. I believe this is S for signature and then R to take something before signature, because T is used for time all the time. So I think RS are just meant to be the 2 parts of a signature. R and S are going to be expressed in 2 B bits. B is the size of your prime number. R is going to be a point on the curve, same as A. It's a different point on the curve. And then S is just some value that is smaller than the prime. And it is going to satisfy this following equation, where 2 to the power C, that was our cofactor, we just called that the cofactor because it's all over the place in these numbers, times the number I pick times my base point, which is a secret, is going to be equal to 2 to the power C, just the cofactor, times R, so a curve point. So I'm taking a point on the curve and I'm multiplying it by something. Then I'm also going to take 2 to the power C times the hash, and now I get to use string concatenation, because as soon as I'm hashing things, I'm just dealing with bits. So I don't care how big they are, I don't care how I put them together, they don't have to satisfy any mathematical properties. I just need to get this information into bits somehow. So I'm going to put R and A and the message inside my hash function, and I'm going to multiply that by A. What does this mean? Intuitively, what is going on here is the public has access to this information. I'm signing it, so I'm releasing the R, and there's a public A, and there's a message. So all of the stuff on this side, the public knows about. Only on this side do we have the problem, which is the public does not know about B, my base point, my secret that I kept that determines whether something is on the curve. So, only I can generate this number easily, but everyone else can verify that it was generated from the message. That's what's going on here. So, only the person with the base point can do both sides of the equation, but everyone else can verify it. That's the usefulness of this. And also, it's really nice that we get to do string concatenation. More properly, should I have called this bit string concatenation? I don't know. I mean, this is a number. This is a number. No one really cares the type of M, right? It's information. It's information that is expressed some way. So they can be thought of as bit strings, but they don't have to be. The EDDSA private key is a B-bit string K, which should be chosen uniformly at random. Do you remember how to choose things uniformly at random? Here, we're gonna review, because I don't want y'all to get in trouble. And again, remember, you're not allowed to do any of this. None of us are. That's not like a you can't do that because you're an undergraduate thing. It's like no human is allowed to do this. Okay. Head dev random. There you go. Okay. Is this chosen uniformly at random? Probably not, but it's not my problem anymore, right? Like, this is the way I was told to generate numbers at random, so if I do it this way, someone else gets in trouble if this isn't truly random, right? So that's good enough. And then if you're in an industry setting, you actually verify this somehow, right? Who determines that these things are truly random? Companies like Galois. So that's what they do. They do cryptography, right? And they make sure things are truly random. Okay, so I'm going to choose a random bit string, B. And then what am I going to do from that? I'm going to generate the corresponding public key, which is S times my base point that I selected. What is S? Well, I take a hash over K, the random bit string I've chosen, and then I take the least significant B bits of that hash, and I pretend they're an integer. Because really, the hash SHA-512 is not giving you back an integer, but it's giving you back something that can be interpreted as an integer because it's 512 bits. So you can interpret it however you want. So I chose something at random. I hash it. I hash it, and then I multiply it by my base point, right? Ah, I clicked left like 40 times. Okay. Do y'all need like a stretch break or something? I know what you need. You need me to do the mini crossword. Okay. Wait, we're only 23 minutes into class. This is the most tired my brain has ever been. Okay.
33 minutes.
Okay, that's fine. We're fine. Word with a pool or wave. Title. Come together. Come together, 5 letters? I was thinking like join. Alto? Does anyone like alto for this? I'm gonna put alto in here, and if it's wrong, okay. Part of D. Okay.
DJ is Dow Jones.
In 5?
Dow Jones
Industrial
Industrial
average?
Yeah.
Do you think it's Dow? No, that'd be great. Well, alto, these might all be wrong. Correct answer sound?
I think that should be like ding.
Yeah.
It's Alto.
I think alto's canceled. Ding, probably?
Yeah.
Swindled? Egg-shaped?
Oval.
I'm feeling good on the ove, which I think literally just means egg. I'm not sure about these last 2 letters here.
You ovoid.
Ovoid? Wait, what? What are you saying? Sorry.
Oh, well, ovoid is a word, but you have an A from title.
Oh, like, that's a word?
Yeah.
Egg-shaped. Oh, is that an adjective? That really feels like a noun to me.
What's the word?
Dictionary says it's both.
Okay. Well, we're further than where we started. Who's Dylan Thomas?
Sounds like sports.
Okay, well, this is Dow then. Diva? What starts with wa? Okay,
Whales?
swindled?
Dylan Thomas is a poet.
From...
That is how you spell whales.
The W is right, the A is not.
Ah!
No, I
Why am I using Vim
He's
motions?
from Wales.
Wait,
So-
no, but oh no, Welsh isn't a country. I lied.
Cringe. Okay. I'm really sad this isn't title. Okay. Come together.
Is
One.
2 what? Yeah.
Sorry, what is this?
2 what? T-U-A.
T-U-A? Okay.
Do you know that, or did you Google it?
I do know
Hell yeah. Why did you let me struggle for so long?
that. On that.
That's fine. This is really looking like tight-ol. Unite.
Yeah.
Okay, so it wasn't.
Ovoid is canceled. I'm putting title back in. I don't know. Wait, sorry. More than one person talking at a time. What is ag?
Yes.
Wow. Good job. What is ovate? That's crazy.
This means egg shape.
That is the fakest word. Oh, it's a clothing store in Quebec. Sorry.
Permanently closed
Wait,
buildings.
does anyone have like a really good French accent to say Quebec? Quebec. I don't know. All right. Well, now our strength is restored. Do you feel like we're back? I feel like we've been back. Okay. Now I know it looks like there's a lot of text on this slide, right? But there's nothing on here that you can't understand if you don't just work through it. Okay. The signature on a message is deterministically computed as RS, the two things, where R is something times the base point. What times the base point? Well, little r times the base point. What is little r? It is the hash of the hash of k, the secret random number, right? Where was k? There it is. Something chosen uniformly at random. So we hashed that, we concatenated it to the message, and then we hashed the whole thing. That's only 2 hashes. That's pretty cheap, right? That's not that expensive, right? Okay. So I compute that, and then I'm also going to compute s. What is s? Well, I'm going to take little r, which again, I just computed, and I'm going to hash big R, which I also just computed. I'm going to hash A. Where does A come from? You can only generate A if you know the secret, right? You concatenate that to M, the message you're trying to sign, and you also have little s. And you just take that mod to the big prime.
How did we find our base point?
Oh, you just choose one.
Oh, okay.
So when I'm deciding, it's your private key, right? So like I use a random number generator I trust, it spits something out, somehow I convert that random input into a place on the curve. And everyone has a different one. Okay. If I do this, then I satisfy this equation, and this equation is the signature verification equation, right? And the modularity here is what sort of clips the curve such that these numbers run into each other and become the same value. All of these are just the same expressions of the same thing we saw in signature verification. Okay. Is this easy? No. Is it possible to understand? Yes, kind of. Would it have been possible to come up with this? Not with my background. I don't know what sort of training people get to be able to sort of intuit that there exists some digital signature scheme that emerges from some properties of curves or something, right? I fundamentally don't know how people like initially came up with these. I'm guessing what happens is you like do a bunch of number theory and then you start noticing patterns, and at some point you get a really good one. A really cool thing about this is that at least nominally, and I don't understand how, all of the operations in here can be done very, very quickly on modern computers, and they also always take the same amount of time no matter which base point you pick. The previous algorithm that is not secure enough, RSA, is specifically not secure enough, not because there's any number theoretic problems, but because it uses mathematical calculations that take different amounts of time based on the inputs, which means that someone can tell at relatively high probability what key you're using, what your private key is, just by seeing how long it takes you to do things. This was relatively insecure. Okay, so that is the Edwards curve digital signature algorithm. And there is an instance of the Edwards curve digital signature algorithm, ed25519, which uses as its hash function SHA-512, which is why SHA-512 was an assignment this term, and which also uses this thing called curve 25519. What is curve 25519? It's this curve that someone found that is fast on modern CPUs. Again, like, who did this? I mean, I know their names, but I don't know how they did this. The people that were doing this had been doing cryptography for a long time before they found this thing. One important thing about this, I think it came into popularity around in the 2005 to 2013 range, and I don't remember the exact number of years in there. After that time, it had sort of already been inferred that at some point we would be going in the direction of elliptic curve cryptography. That seems early to me. I would not have expected that decision to have been made until at least 2008, when computers started slowing down. But some people figured this out and were working on it. The first people to figure it out, work on it, get something out, and popularize it were the NSA, which is Snowden's employer. So the first sort of elliptic curve that made it to the market was developed by the NSA and popularized by the NSA. And not very long after they'd done a pretty good job convincing everyone that they should use this, backdoors were discovered in the algorithm, and this really, really decreased people's confidence in the NSA to be a source you can trust for security. The NSA very clearly designed something that was easy for them to hack. And the thing that I never quite understand about this is, why did they think it would not be easy for anyone else to hack, right? It did not take very long for people to find this backdoor. And now no one will trust the NSA ever again, which they shouldn't have done in the first place. And so now a sort of documented feature of cryptographic algorithms is no one at the NSA has ever touched them, right? This is very good, and it was not really my intention, I didn't design it this way, that both of the examples of why you need cryptography and why this cryptographic algorithm became popular were both about the NSA doing extremely sketchy stuff in between 2000 and 2010, right? That's just what was going on. And then again, I do want to reiterate, my impression is things they've been doing has gotten worse every single year since then and just not been covered in the news. So I don't know how bad what's going on over at the NSA is right now, but I bet it's horrible. So anyways, curve 25519, one of the reasons it was trusted is one of the designers was sued by the federal government for not giving over information to them under pain of going to prison for the rest of their life. So people had much higher confidence that this thing wasn't designed to be intentionally insecure. Anyways, it's named for being over a specific prime field, which is 2 to the 255 minus 19. And so someone looked at that and decided it looked like 25519, which, sure, fair enough. Those things look they have different precision to me, but that's okay. So there's this curve. It looks like this, and I told you I wanted to show you how to visualize it, so this is how I did it. We're zoomed in very, very close to 0 here. If you zoom out at all, well, I guess I'll show you. What was I doing? Okay. So this is what it looks like here. Pretty cool, right? You can kind of see there's a little bit of curving going on. And this is what I tried to draw on the screen. I think I drew something much closer to being a circle on the screen than an elliptic curve. I don't know. Blame my handwriting, right? There's lots of positives and negatives to this, right? The coloration here is just, that is an artifact of how Python has to plot things. I could probably override that. We can clear that out, and we can change our space to be considerably different. So if I just go up to, what am I typing? If I just go up to 1, is this going to work? This is what it looks like if you zoom out at all, which to me is oh, it's just these are basically straight lines. So all of the exciting curvature is happening very close to zero here. And you can zoom out further if you want. Remember, we're working with like huge numbers. Like that's like a pretty big number. What am I doing? Show. There we go. So it continues sort of to flatten out as you get further and further out. So this is just what this curve looks like. And this curve is not yet pushed into the finite field. Okay, I'm introducing two members of this team. I do not think you should be confident in an algorithm because of like who invented it or something, but I do want to give you a sense for just some of the things that were going on while these algorithms were being invented and the people that ended up, developing ones that were emergent. So there's someone named Daniel J. Bernstein. Don't know how to say that. Someone, probably like a senator who was running for re-election, decided at some point that cryptographic technology, so algorithms, like a Python script, should have the same form of classification as like a cruise missile or radioactive material during the Cold War. I'm guessing this has to do with politics. I'm guessing this was not a matter of military strategy because it's about the law and it's about exports, so that's Congress, right? So something changed in 1996. But anyways, what's going on? Before 1996, which is 1995, which is 3 or 4 years after the fall of the Berlin Wall, the breakup of the Soviet Union, and so on. So the world was changing markedly. Bernstein was a cryptography researcher and was basically just publishing results publicly, which is, at least in my understanding, the thing you're supposed to do if you're a scientist, right? So you're supposed to do the scientific method, it's supposed to be peer-reviewed, you're supposed to publish your results. So Bernstein was just studying in this field and got sued by the federal government for basically like selling cruise missiles to like a geopolitical adversary. It's like the same thing. But it was literally just like posting code on the internet. Also, this is the internet in 1995, by the way, so like no one's on there. Anyways, I think this thing went all the way up to the Supreme Court. I could have made this up, but it went up to like a pretty high federal court. And anyways, Bernstein won because no one could figure out why, if you could literally just like say the contents of the code out loud, which you can do, certainly. And I think humans have gotten better at this since 1995. You've heard me unambiguously state code out loud. I'm now able to do that. Required some training. So it's really, really difficult for federal prosecutors to basically convince justices, or judges, they were probably not justices, that this thing shouldn't be covered by free speech if you could say it out loud. So I cannot, for example, say out loud gunpowder. Like you have to fundamentally have physical material gunpowder that has to be shipped around, right? But if I just say something, it's protected by freedom of speech. Anyways, this court case then got passed into case law and then formal law somehow, probably in the forms of like executive enforcement of congressional laws. I don't know. And cryptography sort of regulations have been considerably getting weakened since then. Everyone I know that is involved in this space at all, and in fact, I've been involved in this space. I've talked to, who's our senior senator here? Like some old person who I respect, for the record. Ron Wyden. Like, I've had to be in touch with Ron Wyden's office, been like, Ron Wyden's like sponsoring some legislation to like criminalize symmetric cryptography or something. And I was like, please don't do that. That's colossally stupid. He's like, okay. So anyways, this is like literally constant. Every single academic in the world that understands cryptography has to like constantly be on their elected officials' case because they always think it's good politics to criminalize cryptography in some ambiguous way. That brings me to Tanja Lange, which is basically Bernstein in Europe, I think in the Netherlands. This person's much more active now, and it can be fun to check this out. So step one, oh look, public keys posted publicly on an easily discoverable website. So anyways, if you ever need to get in touch with this person and say something that is extremely secret, no problem. The keys are right here. Here's an RSA key. And here's an ed25519. Yeah, I'm not actually going to use my operating system to do that. Thank you, operating system. Wait, that says Chrome? Crazy. So anyways, you can get those. But it can be interesting to see the kind of things that people involved in this space are talking about, which is basically, I don't know how much news you're following, but the way politics is done now is you essentially say that your political opponents are all pedophiles. And I don't know why this became the way things are being done. But anyways, this means that, like, if you're a certain type of politician, you do the, like, I'm being hard on pedophiles act. And, like, what does it actually do? Usually it's like some form of extension of government surveillance. So then a bunch of scientists have to go out and be like, okay, in addition to not being pedophiles, we also think you shouldn't criminalize privacy. And so that's what these letters say. And so this is going on right now. This is last year, right? Probably I signed this. I don't know. And that's fun stuff to look at. Also interesting to see what technologies people use to document this, right? So it's all based outside of, like, research organizations. So anyways, thought I would give you a sense of some of the characters behind this. I think it was a team of 5, and I think only 5 of them have, like, a major public presence. But they're all essentially, like, full-time privacy advocates in addition to being cryptography researchers, which is kind of interesting. I don't know actually, like, which way that goes. Like, you get really into privacy and then really into cryptography, or vice versa. There's one other thing. Oh, I thought I corrected this. Those 5s are supposed to be superscript. I thought I fixed all of them. I caught this error at some point, but they're supposed to be superscript. Okay. ed25519. The 25519 is 2 to the 255 minus 19, and that is your prime value, which means that this is your prime field. Or rather, your finite field, which is also a Galois field, which is defined as a prime blah, blah, blah. This is the Twistors-Edwards curve we take. Earlier this class, I told you that Edwards curves were of a certain form, and specifically it was a factor. I had an a written here, times x squared plus y squared, and that was supposed to be equal to 1 minus, and there was a d here. I don't know what d was supposed to stand for. So this is basically the Edwards curve where we set a equal to -1 and d equal to this fraction. Somehow this corresponds to curve 25519, and the math was, like, non-trivial, so I'm not showing it to you. But if you look at this thing, you know how to plot this. This isn't the hardest thing to plot in the world, and I think I do it on the next slide. And also, like, this is, like, pretty understandable, right? So you know, for example, you can't just, like, throw a bunch of zeros in here, right? But I think if you, like, set x equal to 0 and y equal to 1, it's, like, totally fine. Or it's, like, very, very close to being fine. You might have to do a little bit of rounding. This is what it looks like, which is, like, not too exciting. I think I have this set up so the vertical is x and the horizontal is y. So basically at all x values, you have a number very, very close to 1 in absolute value. You either have a positive or negative. And there's slight variation in here. I think it's just very, very hard to perceive. And in fact, we can probably perceive it here a little bit. Do I trust myself to get this? Yeah, okay. I'll grab this. I'm going to do all the imports again. Okay. Rather than plot, okay. Here's f of x. And here's the 0th entry in f of x. And then here is, how do I do this? I think it's like that. I'm trying to remember how NumPy works. I'm sure it was that. That's what I did already. Okay. So, let's see. F of x What is this? A lot of brackets at the end. We'll make the lin space smaller. That'll be easier. I'm going to knock this down to 50. Take f of x. Okay. So what's going on here? This is a pair of arrays, one negative, one positive. Why is that? Because there's the positive and negative solutions when we square. I can take the first one of these. I'm so surprised it doesn't look like this. Okay, and we get the negatives, or we get the positives. Okay, so we can just take one of these, and then we can plot, let's see, f of x 1. And then you can see a little bit of the curvature better. So there was a curvature hiding in there. It was just very, very close to being 1 in absolute value the whole time. So I don't know how you want to look at this or investigate this, but fundamentally it looks something like this. Fundamentally it also looks something like this. I don't know. They're curves, okay? And curves can look a lot like lines without actually looking like them. And so that is our curve that we've defined for our Edwards, blah, 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 25519. Okay. This is the large prime, and I think I fit it on this slide, but you can also just look it up, and it's present in other places in the course materials. By convention, we're sort of following the thing that everyone's been doing this whole time, which is it's like really, really nice to find primes that are close to powers of 2. So we have a prime that is a little bit less than a power of 2, and we have a prime that is a little bit more than a power of 2. Does this look like a little bit? Maybe not, but this number is enormous, right? So adding even a large number of digits to that is like really not moving the needle in all of this. And I think I can demonstrate this to you mathematically as well, which is if I look at the hexadecimal representation of 2 to the 252, it's that many digits. And if I look at the hex representation of this, it's that many digits, so I can add them together. And we still have an enormous number of intermediate digits, right? So this is, I would argue, in some sense, close to being a power of 2, right? The probability of being this close to a power of 2 is very, very low. So they picked something that was very close to the power of 2. The cofactor is 3. That's nice because it's small. Why is it nice for this thing to be small? We've got to multiply these numbers by each other. We're going to raise 2 to that power for the cofactor. So remember, we're multiplying 2 to the power of the cofactor, which is 8, times the large prime. I got to throw some parens on here. What is the nice thing about that? That fits in the same number of bytes. This still fits in 256 bits, which is... Oh, can I divide 256 by 8? Surely I can do that. No, I can't. I'm not right now. Okay. 32. I knew that for sure. So it still fits in 32 bytes. And it fits in this many words. So you only need 4 words to fit this in. 4 U64s. So that's kind of cool. Okay. That's definitely wrong because it's 255, right? It's 8 words. Okay, so if that were 4 instead of 3, we would have a huge problem where we would have to go up to using 1024 bits at a time because we're probably going to need a power of 2 bits. This is kind of weird, but all of this stuff is defined by the algorithm. ed25519 is the choice that satisfies the algorithm EDDSA. What that algorithm produces is a signature scheme. A component of that signature scheme is how you select your private key. This is how you generate the private key. The base point is a component of the private key. So what do? You pick a number, and the number satisfies these requirements. It's a unique point such that its y value equals 4 divided by 5, and it has positive x. Now, I didn't quite expect this, but they actually define positive and negative differently in the context of this field, but they just mean even versus odd coordinates. I think that's pretty much the same thing we did in NumPy, where I just took one of the two things. And I don't know that I actually selected them appropriately, so least significant bit cleared versus most least significant bit set. I didn't look at the bits. I don't necessarily know how they were dealing with that, but that's not too bad. You're just going to pick one of them. And if you look at the bit value and it has the least significant bit set, pick the other one. And then the hash value, and this was extremely convenient. You can use the hash value of SHA-512, which is why that C matters so much, right? You get to use SHA-512, which is already fast on modern devices. So that gives you a bit size of 256 and a hash of size 2B. So that's ed25519. Not bad at all. I don't know why I said it's not bad at all. It's awful. It's like one of the hardest things to understand in the world. But that's okay. So here's some takeaways. I thought I'd give you some takeaways because I feel like I made you stare at a lot of equations today. But I don't really feel bad about that. I think if you stare at equations enough, you'll build up stamina and then be able to do it more comfortably. So we'll find out. But, okay. EDDSA is a combination of equations that requires a choice of constants. ed25519 is a uniquely good choice of constants. Together, what this basically does is it's an engine that allows you to produce private keys that can be used for public-private key crypto systems, right? A public key tells someone how to encrypt something for you, and then only the corresponding private key can decrypt it. This is used in Bitcoin, Git, and e-commerce. Do you have a question?
No.
Okay.
Sorry, I scratched.
That's good. My claim is that the best way to understand ed25519 is to implement it. I do not think this is true of every crypto system. I do not think this is true of RSA. I do think this is true of SHA. The reason I believe this is when ed25519 came out, it was released with 4 Python files that are still publicly posted. And I'm not used to seeing that. And I just took the Python files and I ran them, and they exploded because they were written in Python 2. So then I fixed them, and then I put some like really, really heinous code design decisions in there that I like doing for fun in there that I'm going to make you look at. So you are either welcome to use my Python that is correct but contains code written by Calvin, or you can use the released version in Python 2. I'm providing them both for you. Take a look at them, and then write it in Rust. Okay. When I say write it in Rust, what do I mean? Lecture is over. Lab is starting now. This is the lab for today. Is it going to load? Did I not click it? I didn't click it. Okay. Oh, I have to make you say the pledge again. Okay. Raise your favorite hand, if you're able, and repeat after me. My code is bad and wrong, and I will never use it.
My code is bad and wrong, and I will never use it.
All code provided for this class is bad and wrong, and I will never use it.
All code provided for this class is bad and wrong, and I will never use it.
Ideally, no one would ever use any code ever.
Ideally, no one would use any code ever.
But if I must use this code, I will use a documented, known library.
But if I must use this code, I will use a documented, known library.
Okay, that's all. Thank you. Never use this code. There's a disclaimer on this website that says never use this code. And I copied the code. See, it says it doesn't include protection against attacks. That's literally the only thing it's for. This is the protection against class attacks code, and it doesn't have protection against class. Okay. There's 4 files on this page. I'm going to go back and forth a bunch. 1, 2, 3, 4. Apparently, it's covered by all of these patents, which they made sure expired before they released it. So here's some code. Oh, I used the black formatter, which is, I guess, the industry standard Python formatter. So I hadn't used it before. I wanted to format my code because, like, this was very old code. And something that was really cool, it seems like they throw in double new lines between every function. So maybe you'll see that in production code. I presumably had seen this before and hadn't thought about it. Okay, here's my code. This is basically constant generation. Oh, this is more lines than I remembered. This doesn't look bad, though, right? That's 129 lines. I'm not going to feel bad about that. Okay. Here's a series of assert statements. This should all be true. This file is really fun to look at, actually. I think this is really cool, right? You can zoom out. So they provided a ton of regression tests for this.
Sorting algorithm?
No, so this is, why did I click that? Oh no, okay. This is the private key, this is the public key, this is the message, and this is the signature, I think. So the message is included in the signature, and they do different lengths. So the first line is length 0. I took the second line. I gotta stop using my hands to do things. But in theory, every single line in this file can be used to test this code. What did I do? I provided one line. This is the second line. And then this code eats a line, and I defined the line up here. And then it demonstrates that all of the agreements are satisfied, that something can be encrypted and then decrypted back, and its signature can be satisfied. So, your job, nominally, the way I had this originally scheduled, and it doesn't matter what the scheduling is, today in class, you would understand this. So there's not a lab exercise. I gave you some check marks.
That's the Hamming.
This is Hamming weight. I don't know why I'm in Hamming weight. Okay. Oh my gosh. Okay, I gave you these 4 check marks. But really, the 4th one is the start of the homework. And then the homework is, want to sort of guide you through this. Implement ed25519 and then never use it ever, right? Just understand how it works. The thing that makes it secure is actually also extremely interesting and could be an entire separate class. I've been really wanting to teach a side channels class here, and it's very hard to do that because then I would have to understand side channels, whatever those are. But I didn't know how much scaffolding to give you, so I gave you what I think is a reasonable amount. This is constant generation, but it only works once you implement the functions. But I thought this was nice because this includes a bunch of examples of how I expect your code maybe to end up looking. So I'm using, for example, the BigInt library, and I'm using Euclid. What is Euclid? That's Euclidean division, so division and remainder. Here's a way to put pretty big numbers into BigInts. I don't know, things in here that are potentially useful. This is a way to use the import statement. So I wanted to give you some code to get you started. In CS1, you would get this from your section leaders. Now you're getting it from me. And then here's an example of one hard-coded test case. I wasn't sure you would be super comfortable typing this number into Rust. And of course, I typed it into Python and then had the Python write the Rust. You can do whatever you want, right? But anyways, this is how you include that. And you just see, I take a vector of I think these are U8s. And it's just I take a byte at a time, and this is pretty long, but it's not that long, right? I don't know what I'm doing. I went back by accident. You know how sometimes your computer does things that you tell it to instead of what you mean? Okay. So you can either use the empty string or you can use 72. I used 72. Then you generate the public key, you create the signature, you verify the signature. This is what my cargo.tom's obvious markup language looks like. You're probably not used to seeing cargos that look like this because this has a ton of dependencies in it. You can also use your IX and your SHA. That's fine. So you don't have to use this stuff. You've written things that can do all of this stuff. And I have hex here, but you also have the midterm on this stuff, right? So you know how to deal with all of this. So these are the libraries that probably normal Rust people would use. And then I gave you all of my function types. I played around with function types a little bit. You shouldn't necessarily consider yourself having to implement it this way, but I certainly would because this is how I implemented it. So you can go ahead and take a look at this. Okay, so get started on that somehow and get started with me here. I'm going to take a 5-minute break, and then I will start wandering around the class asking you how you're doing. Ready, go. Oh, I'm going to turn off the stream too.